Hello and welcome back. This section will talk about hyperbolic functions, definition hyperbolic functions. Hyperbolic cosines of x is e to the power of x plus e to the power of negative x divided by 2, and hyperbolic sines of x is e to the power of x minus e to the power of negative x divided by 2, and so on. These are, and hyperbolic tangent is same thing as like tangent. Hyperbolic tangent x is hyperbolic sines x divided by hyperbolic cosine x. And you have it, same thing for hyperbolic cotangent x. So basically there is a similarity between hyperbolic function and trigonometric function itself, okay? So we are asked to deriving hyperbolic identity, use the fundamental identity hyperbolic cosine square of x minus hyperbolic sine square of x is equal to 1 to prove that 1 minus hyperbolic tangent square of x is equal to hyperbolic secant square of x. So we are asked to use this identity. So let me write the identity, which is hyperbolic cosine square of x minus hyperbolic sine square of x is equal to 1. So, you have to think. You already have some identity right here. Just think about it. You already know uh, hyperbolic sines divided by hyperbolic cosines would give you what? Hyperbolic tangent, right? So, or you can see tangent right here. So the good thing I can say is, what if I divide both sides by hyperbolic, everything by hyperbolic cosine square? Look, and I will tell you why I'm doing that. So I divide each term by that. And then why I did that, because I can see this one will give me hyperbolic tangent square, which is what I have. And this one would be 1, right? And 1 divided by hyperbolic cosine square also is what? Seconds, hyperbolic secant square. And that's the proof. So we can see we have 1 minus hyperbolic tangent square of x is equal to hyperbolic secant square of x, and that's it. Okay, and then for b, we are asked to derive the identity hyperbolic sines of 2x is equal to 2 times hyperbolic sines x times hyperbolic cosine x. So again, to prove this one, what do we know so far? We know, based on the uh, definition of hyperbolic function, we already know uh, hyperbolic sines of x is what? E to the power of x minus e to the power of negative x divided by 2, right? And hyperbolic cosines of x is what? E to the power of x plus e to the power of negative x divided by 2. So based on this one, of course, hyperbolic sines of 2x will just be what? We are going to replace anywhere we will see x by 2x, right? So we'll have e to the power of 2x minus e to the power of negative 2x. Everything is divided by 2. Or, e to the power of 2x minus e to the power of negative 2x is nothing else but e to the power of x minus e to the power of negative x times e to the power of x plus e to the power of negative x. If I distribute this one, I will get exactly this. And everything would be divided by 2. But if I check correctly, this is what? This look like hyperbolic sines x. But since hyperbolic sines x is divided by 2, and this is not divided by 2, so we can say this is what? 2 times hyperbolic sines x, right? And this is what? This look like hyperbolic cosine x, but since it's not divided by 2, we can say this is 2 times hyperbolic. So what I mean is this is like 2 hyperbolic sine x, and this is like 2 times hyperbolic cosine of x. So 2 times 2 is what? 4, and 4 divided by 2 is 2. So of course this one will give us 2 times hyperbolic sine of x times hyperbolic cosine of x, and that's what we were trying to prove, and that's it. Okay, so again, let's move on. These are the hyperbolic identities. I want you to read each of them, like hyperbolic cosine square of x minus hyperbolic sine square of x is 1. It does look like trigonometric identities, but not the same. You can see on trigonometric identities, this is plus, not minus, right? Cosine square of x plus sine square of x is 1. But for hyperbolic identities, cosine square of x minus sine square of x is equal to 1. It's easy to prove, okay? All of this is easy to prove. You just need to use the definition to prove them, okay? I don't want to spend time on proving here because you will not be asked to prove. But again, to prove the first one, what do you need to do? You know, it means e to the power of x plus e to the power of negative x squared, divided by 2 squared minus e to the power of x minus e to the power of negative x divided by 2 squared should give you at 1. If you expand everything combined like them, you will see it will give you 1, and that's it. Okay? You can practice this as your algebra at home. But this is the trigonometric the hyperbolic identities. And after that, we have the theorem, derivative, and integral formulas. So the derivative of hyperbolic cosines of x is what? Hyperbolic sines of x. So which means the entire derivative or the integral of sines hyperbolic of x dx is hyperbolic cosines of x plus c, and so on. And the derivative of hyperbolic sines of x is hyperbolic cosines of x, which means the integral of hyperbolic cosines of x dx is hyperbolic sines of x plus c, and so on. Based on that, we are asked to evaluate the following derivative and integral. So first thing, find the derivative of hyperbolic secant of 3x respect to dx. So again, to find this one, do not forget the hyperbolic secant of x is given to us. That's the basics one, and this is what the chain rule, right? So this will just be what? Negative 3, right? Second, hyperbolic secant of 3x times hyperbolic tangent of 3x, and that's it, right? This is my derivative. And b, you can see if I'm asked to find the second derivative of hyperbolic secant of 3x respect to dx squared, Of course, we have to find the derivative twice, right? We already have the first derivative, which is right here. This is the first derivative. So I'm just going to find the derivative of that as well. So we need to find the derivative of -3 hyperbolic second of 3x times hyperbolic tangent of 3x. You can see to find this derivative, we have to use what? Product rule. If you do remember, because we have the product of two functions, all right? U and V. So which will be the derivative of U prime. So the derivative of negative, let me push this one a little bit to the end. The derivative of, I need to put my glasses. Okay. So again, the derivative of uh, -3 second, hyperbolic second of 3x will give us what? That will give us 9 second, hyperbolic second of 3x times hyperbolic tangent of 3x, right? That is the derivative of u prime times this tangent, hyperbolic tangent of 3x. Let's not forget that, right? Then plus still -3 hyperbolic second of 3x times the derivative of hyperbolic tangent of 3x, and the derivative of hyperbolic tangent of 3x is um, 3 hyperbolic second square of 3x, right? Now the rest is algebra. I'm trying to simplify. So I will have 9 hyperbolic second of 3x times hyperbolic tangent square of 3x, because if I distribute this one, this times this will be square. And then minus 9 hyperbolic second cube of 3x. You can leave it like this, or if you want, we can factor 9 and sinus hyperbolic of 3x. Okay, that's it. So now see, to find the integral of hyperbolic cosecant square of square root of x divided by square root of x dx. As you know, there is no quotient rule or product rule on finding the integral, solving an integral. So far we have to use what? Substitution. So I would just say right here, let u be equal to square root of x. Then, the derivative of u would be 1 divided by 2 square root of x dx. Or, this means to integrate my cosecant, hyperbolic cosecant square of x. I can write this one as like this, 1 times square root of x dx. You can see there is no 2 right here. There is no 2. but we have it 2, so I can multiply both sides by 2. Basically, what I mean is this is mean what 2 du will be equal to 1 over square root of x dx. So now doing my substitution, this is same thing as what? The integral of cosecant, hyperbolic cosecant square of u, right? But 1 over square root of x dx is what? 2 du. So that's why we'll have a 2 right here outside the integral. And then du, right? So the 2 du is right here. So now we can go ahead and find the antiderivative of this one, which would be what? The integral of hyperbolic cosine square of u du would be what? Negative 2 hyperbolic cotangent of u plus c. But what is our u square root of c? So my final answer would be negative 2 hyperbolic cotangent of u means square root of x plus c, and that's it. Okay, same thing for d. Will not change. Again, there is no product rule on integral, right? So we can see we have two hyperbolic function, but the highest power is hyperbolic sines. So in that case, we will just say let our u be equal to the highest power, which is hyperbolic sines of x. Okay, then du will be what? What's the derivative of hyperbolic sines x? That is hyperbolic cosines of x dx. And you can see that's exactly what we have. But once we use substitution, we also will be changing the integration, the limit of integration. So you can see when x is 0, then our u will be what? Hyperbolic sines of 0. And you know, that will just give me 0 because it will be e to the power of 0 minus e to the power of 0 divided by 2, which is 0 divided by 2, which is 0. And when x is ln of 3, let me move this a little bit back because we need more space. When x is ln of 3, then our u will be what? And our u will be hyperbolic sines of ln of 3. Of course, which will be e to the power of ln of 3 minus e to the power of negative ln of 3 divided by 2, which would be 3 minus 1 over 3 divided by 2. So if you simplify this one, you would see it will give you 4 divided by 3. So that being said, to find the integral from 0 to ln of 3 sines hyperbolic sines cube of x times hyperbolic cosines of x dx. By doing my substitution, it will be same thing as the integral from 0 to 4 over 3, right? u to the power of 3 du, which will be 1 over 4 u to the power of 4, 0 to 4 over 3. Which would be 1 over 4, 4 divided by 3 to the power of 4 minus 0 to the power of 4. And if you do all the calculation, you will see this one will give me 64 divided by 81. And that's it. Okay? I hope you are enjoying hyperbolic functions. So now next, we are going to talk about some theorem of integral of hyperbolic function. So if I'm asked to find hyperbolic tangent of x dx, that is ln hyperbolic cosine of x plus c. Hyperbolic cotangent x dx is equal to ln absolute value of hyperbolic sine of x plus c. Hyperbolic secant of x dx is equal to tangent inverse of hyperbolic sine of x plus c. And integral of hyperbolic cosecant of x dx is equal to ln absolute value of hyperbolic tangent of x divided by 2 plus c. So we are asked to solve this example. Find the integral of x times hyperbolic cotangent x squared dx. So you see, what did I say? X squared dx, right? What did I say? X squared dx. So you don't get confused. Okay? When you see x squared, you have to know these two are not the same. This is different from, in this one only x is squared, but in this one the whole function is square. In this one the whole function is square, but in this one only x is square. So don't get confused, okay? It's two things different. But again, do not forget we don't have product rule, so we still need to use what? Substitution. So to find this one again, I would just said let u be equal to x squared. Then du will be what? 2x dx, which means 1 half du will be equal to x dx. So we will do our substitution again. So that means if I'm asked to find the integral of x, hyperbolic cotangent of x squared dx will be equal to, by doing my substitution again, of course we said u is what? X squared. So that will give me hyperbolic cotangent of u, but du is what? 2x dx. So which means x dx, because this is x dx, right? So that's why I would put my 1 half outside, because that's a constant, and then du right here. And then what is the integral of hyperbolic cotangent? We just talked about it, right? Is ln absolute value of, so this one will give me 1 half ln absolute value of sine hyperbolic of u plus c, right? But since u is what, x squared, so my final answer would be 1/2 ln sine of x squared plus c. Of course, sine hyperbolic sine, not sine hyperbolic of x squared is greater than or equal to 0. Any question? If you have question, pause the video and then go over it again, okay? So now we have this theorem. Theorem, inverse of the hyperbolic function expressed as logarithm. So you know the inverse of exponential is what? Logarithm. So of course, hyperbolic function are represented with exponential, so their inverse would be logarithm, right? That makes sense. Okay, so inverse hyperbolic cosine x is what? ln of x plus square root of x squared minus 1 with x greater than or equal to 1. Inverse hyperbolic sine of x is ln parenthesis x plus square root of x squared plus 1 and so on. So these are what? The inverse, right? And then we have the derivative of inverse hyperbolic function and the integral as well. So the derivative of inverse hyperbolic cosine of x is what? Is equal to 1 divided by square root of x squared minus 1. X is greater than 1. And so on. The derivative of inverse hyperbolic sine of x is 1 divided by square root of x squared plus 1. And the derivative of hyperbolic tangent inverse of x is 1 divided by 1 minus x squared, absolute value of x less than 1, and so on. So these are the hyperbolic the derivative, and we also have the integral. So you know, if you know the derivative, you should be able to do the integral as well. So if you see, so this is really important to know, because you know, as you know, there is no quotient rule, there is no product rule for integration. So sometimes by looking at it, you should know if you have inverse hyperbolic function. Okay, that's very important. Okay, so you can see the integral of dx divided by square root of x squared minus a squared. So if you have this form, you need to think about what? Inverse hyperbolic of cosines, which would be inverse hyperbolic of cosines of x divided by a plus c. And if you have the integral of dx over square root of x squared plus a squared, that's the inverse hyperbolic sine of x divided by a plus c for all x. And this is tangent. So for tangent, you need to make sure the absolute value of a, when the absolute value of x is less than a, and when the absolute value of x is greater than a, which would become hyperbolic cotangent inverse, and so on. So let's do these two examples for that. A, we are asked compute dy over dx for each function. We have y is equal to tangent inverse of 3x. So we are asked to find dy over dx. So in this case, my dy over dx would be what? Finding the derivative of inverse hyperbolic tangent of 3x dx, which would be, do not overthink, it would be 1 divided by 1 minus 3x squared times, what's the derivative of 3x? 3. So you simplify everything. So this one will give me 3 divided by 1 minus 9x squared. That's it. Okay, it's right here, right? So this is the basics one. But if you have to, if it's not x, do not forget to replace x by anything you have. Okay. For b, we have to use, to find the derivative of b, we have to use what? The product rule, right? So to find, again, dy over dx, it will be finding the derivative of x squared times inverse hyperbolic sines of x dx. So in this case, we have the product of 2. So to find the derivative, we have to use the product rule, which is u times v, right? So this derivative would be, first thing, the derivative of x squared is what? 2x times the inverse hyperbolic sines of x, then plus the x squared times the derivative of inverse hyperbolic sines, which is what? 1 divided by its square root of x squared plus 1, right? And then, of course, you can rearrange this one, or you can leave it like this. So you can factor x, or you can leave it like 2x inverse hyperbolic sines of x plus x squared divided by square root of x squared plus 1. Okay? So the choice is yours. If you want, you can factor x. So last, not the least, we are asked to compute the following integral. Okay? Compute the area of the region bounded by y is equal to 1 divided by square root of x squared plus 16 over the interval 0, 3. So the region bounded by this one will be finding the integral from 0 to 3, right? 1 over square root of x squared plus 16 dx. Or we can see this is same thing as if you multiply 1 by dx over. So which is what? Inverse. This integral would give us inverse hyperbolic sine of x. So which would be inverse hyperbolic sine of x. And my a in this case is 4, right? So x divided by 4. From 0 to 3. So which would be sine, inverse hyperbolic sine. If I substitute 3, so 3 divided by 4 minus inverse sine hyperbolic of 0 divided by 4, which is 0. And since hyperbolic inverse of 0 will give us 0, so the final answer would be right. Again, you can evaluate this one using your calculator as well to approximate. Or you can use this inverse hyperbolic sine of x to find the exact value as well. So we can do that even if we are not asked. We can see inverse sine hyperbolic. Okay. No, I always forgot about the h. Of 3 divided by 4 will just be what? ln of x. X is what? 3 divided by 4 plus square root of 3 divided by 4 squared plus 1. And 3 divided by 4 squared plus 1. If you check your calculator, this one will give me 9 divided by 16 plus 1, which is 25 divided by 16. Square root of 25 divided by 16 is 5 divided by 4. 3 plus 5 is 8. 8 divided by 4 is 2. So the exact value is ln of 2, or you can approximate, okay? So the last part for this section is evaluate the integral from 9 to 25 dx over square root of x times 4 minus x. So let's go ahead and do this one. So if we look at this one does not match any of the formula we have in the previous theorem, right? So we have to use what substitution. So since it involves square root of x, that's the only power we see here. We will have said that let u be equal to square root of x and try to rewrite this one based on that. Then du will be what? 1 divided by 2 square root of x dx, right? So we are going to use our substitution. So of course, if u is square root of x, then u squared would be what? X. because we have x right here. Let's not forget we have x right here. So if we said u is square root of x, then we know u square will be what? X, right? That makes sense. So by doing my substitution, and I also know if, or before even I write this one, let me, if x is 9, then u will be what? Square root of 9, which is 3. And if x is 25, u will be 5. So we know we said u is square root of x because we see x right here. So this means u squared will be x. So by doing this substitution, we will see our integral, which is 9 from 9 to 25 dx over square root of x 4 minus x can be rewrite as this one, because I want you to see, get used to substitution. You need to really practice this. This is same thing as 1 divided by 4 minus x, right? Times 1 over square root of x dx, because I want you to see this one. So we have du, right? But we need to multiply by 2 to get 1 over square root of x dx. So that is why we said this is exactly the same thing as doing my substitution. 2. Now the limit of integration would be from 3 to 5, right? 1 divided by 4 minus u square du, which is same thing as du divided by 4 minus u square. And then what is this? This is what? Anybody? This is inverse hyperbolic cotangent, right? And what is my a? 2. So we already have these 2, and the antiderivative of this one is 1/2 inverse hyperbolic cotangent of u divided by a is what? 2. From 3 to 5. 2 times 1/2 is 1. So my answer would be, we substitute, we will have hyperbolic inverse of cotangent of 5 divided by 2 minus inverse hyperbolic cotangent of 3 divided by 2. And that is my final answer. So again, you can go ahead and try to find the approximate value using either the inverse hyperbolic cotangent, or you can also use sometimes you would be using some identities. Okay, so this is what I was trying to teach you in this section. I will see you in the next one.